All right, so now we're going to observe vector fields by integrating streamlines. Okay, so we're going to define this Lorentz thing, which gives us, which parameterizes this vector field, okay? For for this example. Then we're going to define P. And then here we specify the parameters of the Lorentz partial the Lorentz differential equation. And then we apply. So what is VF? VF is like a vector field, okay? So let's plot it. Stream plot VF, grid size 10 by 10. Oh, grid size equals, okay? So this is from the Lorentz differential equation. When you pick like certain parameters for the differential equation, then you get a vector field like this, okay? When in a certain range of, in like a when the range of values is like within this cube, okay? And in the text here, you can't really see. You can just see a two-dimensional depiction of it, but when you have the interactive session in Julia here in the computer, you can turn it around and get a view of it, you know what I mean? Using the mouse, you click around a little bit, and the keyboard controls are there as well if you want to use the keyboard to manipulate it. Well, that's just the Mackie software, you know, visualizing streamplot. Anyway, I'm getting carried away. But the point is that this is a numerical representation of a vector field, and any vector field that we numerically represent can be plotted here. And so one of the things, examples here is the ODE solver in the Adapode package. So this is built on Cartan as well. Provides both the Runge-Kutta and multi-step methods with the optional adaptive time stepping. So let's do an example of that. So we'll define the function as like this, 10.0, right? 60.0, 8/3. And then we'll define x0 then we'll define the initial condition. Okay. So this produces like an initial condition object for the differential equation solver, okay? Once you have an initial condition object, then you can, you know, solve a differential equation, right? Then we just pick a solver, multi-step integrator, fourth order, 2 to the minus 15 step limitation. All right. So that solves the, gives a solution. And how does this work? Well, we're just visualizing it with the Mackie software, but if you just run ODE solve by itself, this produces a Cartan TensorField, okay? So all these things are tensor fields, Cartan tensor fields, okay? And the Grassmann package is used as the foundation. Like all these vectors and stuff, they're Grassmann elements, okay? They're three-dimensional vectors in Grassmann algebra, okay? And then the whole solution of the differential equation is a tensor field in the Cartan package. And the adapode package has a differential equation solver, okay? As an example, like, so if we integrate you know, it uses this approximation, you know, to do that. Anyway, let's move on to the next example. Not get too bogged down on every single example. So we now have a square domain. We do something similar to the diameter, but now it's going to be a disk. And what happens when we integrate that disk, you know? It's pi, of course, right? So this is what we've set up here. So this is just to show that you can calculate this integral, you know, of 1 basically, right? And that gives you the number pi, right? Because it's the area of the circle, but it's in yeah. So it's a nice calculation that helps verify that it works. And let's go on to the cube. So we integrate the ball and we get 4.19146, and 4 pi over 3 is 4.18. So it's a pretty nice approximation. Let's look at the volume of the ball. Or oh, I may have to. Oh, I was working on that the other night. Anyway, we don't need to visualize the ball right now. It's not a big deal. But I thought I set that up correctly, but that'll be fixed in the next version. It's always an easy fix. It's no big deal. It's gonna be working. All right. So now we have the hyper area of a hypersurface. So let gamma be with a subset of x from Rn to Rn plus 1 be a parameterized hypersurface, which is a boundary of omega, which is gamma of x. Okay? And since the pullback of gamma star 1 is determinant d gamma, we can apply these really nice integral things, relations. So this is a theorem. Okay, so we have the integral of over the boundary of omega. Okay, and that's the integral of gamma of x, like the integral of 1 of gamma of x. Okay, right? But then this is with the pullback, the integral of x. Okay, so now we use a parameterized hypersurface to calculate this, and it's the absolute value of the determinant of this exterior product. Okay, and x can be parameterized as a1 to b1, you know, if it's like a grid like this. The disk circumference and the sphere spat. So let's try those out. So that's our typical circle, right? And so what happens when we take the surface area? So we know that these are two different calculation techniques. Like, they give you pretty much the same answer, but total arc length calculates it one way and surface area calculates it another way. And it looks to me like the surface area approach actually has a smaller error. Okay, so this is the wireframe of the sphere, and we can calculate the surface area like that. So yeah, 12.533. So that's pretty good. And for circ, compare it with 2 pi. So that concludes that example. So let's get to one of the more interesting results in this paper, which is the sector integral theorem. And I haven't seen this before anywhere else, so I think this is a new theorem. I don't know if it's been, you know, discussed somewhere else that I'm not aware of, but to me this is a new theorem that I found. So it expresses this kind of generalized sector integral. So when x is like a subset of Rn and gamma is a parameterized hypersurface like previously, with gamma of x being parameterized in this way by x, and it's the boundary of omega. Well, the point is that there must exist some omega defining the sector of the hypersurface gamma of x with scale rho equals 1. So the question now is about what's that omega, and it's the integral, and what's the integral of it, right? So there's some omega and the integral of, like, we have this integral 1 over n plus 1 times the wedge product of the integral of the wedge product of gamma and d gamma dx1 and d gamma dxn. That integral equals the integral of 1 on some sector, and omega is the sector of the hypersurface, okay? And this is like the sector integral, and this is like this is like a formalism. So I have the proof here, so you may not understand why like this sector integral theorem is a thing, but it's because of this. First of all, because we can prove it in the following, and then it shows up in various calculations, and so that's why in the Cartan package. So because it shows up in various calculations, I figured that I discuss it like as a theorem and give the proof of it and so on, and how to think about it. So all right. So if we'll consider a function like f, which is from 0 to rho and the product with x, like this is a product space from 0 to rho and x to Rn plus 1, and it's defined like this: f of x0 to xn equals x0 times gamma of x1 to xn, okay? So it extends the function by adding another parameter to it, and now we want to take the integral from 0 to 1 of that the determinant of df, okay? And this expands out integral of 0 to rho x0 to the n gamma wedge d gamma dx1 wedge d gamma dxn. And now we have to take the integral of this from 0 to rho, and that makes it so that we have rho to the n gamma over n plus 1 wedge d gamma dx1 wedge d gamma dxn. And so this result then can be applied with a pullback, okay? So since the pullback of f is determined df, then the domain omega is actually f applied to 0 rho to x, and we're going to set rho equal to 1 actually, but with a new variable. So that means that the integral of 1 over omega equals the integral of f of 0 rho, the product of 0 to rho and x, okay? And so we can use the pullback. All right, so now we have the integral of x and 0 to rho, so we can split up the domain, because you know how this is the product space, right? 0 to rho and x. So that's why we split up this integral now. And because we know what the integral from 0 to rho is, we now have the integral over x, okay? Because we evaluated this already. And now we can rewrite this using this notation, okay? So hence the integral over 1 of the sector omega is the sector integral covering gamma of x, by parameter x. So yeah, I found that's quite interesting. So let's do it. Let's do sector, integrate, circ. Okay, so we can see now that doing the sector integral is a nice way to compute. Like we just apply the sector integral, and then that gives us the volume of the like sphere is just like a surface, right? So we have this parametric surface of a sphere, and if we take the sector integral of it, like I talk about in my theorem, then that gives you the volume of the sector inside of the surface. Okay, and that's the sector is like that inside of the sphere. But the sector integral theorem is like more general, like this doesn't need to be necessarily a closed surface, I guess, but it'll still produce a domain, a sector. So there's a lot more to it with the sector theorem and stuff, but let's just keep it moving. So what about the link number example? So we have to define the link map of two space curves instances f of t and g of s as parameterized hypersurface link s of t equals g of s minus f of t. So we have the link map, and as a corollary of the sector integral theorem combined with the unit link map, we have the following integral: 1 over 4 pi of gamma of the sector integral thing equals g of s minus f of t divided by the absolute value of g of s minus s of t cubed, and then the dt dg and dg ds. And what's interesting about this is that this is 4 pi over thirds, so you can divide this by, it's the sector integral of the unit link map divided by 4 pi over 3. So that's the volume of the sphere, okay? So the link number is the sector integral modulo the sphere, okay? When the evaluated with a parameterized hypersurface, gamma of s is the link map, the unit link map, okay? So the link number defines the sector integral of gamma of x by the volume of ball. Let's try out some examples. So here's an example with two curves, f of t and g of t, and they're just circles in this situation, but they're circles oriented in three-dimensional space. And now what we want to know is what's the link number of those. And it should come out to 1.0, but because this is like a approximation, it's not exactly 1.0. It's a approximation of a numerical approximation of an integral. And we can also look at visualize what the link map looks like. So we had those two curves, and now we have the link map, which is of those two curves. Okay, so this is the surface that's being integrated in this link number example using the sector integral theorem, okay? And link number gives you the actual link number, okay? But link map helps us look at what the surfaces look like. Then we have the Gauss curvature. So it's alternative formulas for extrinsic Gauss curvature Ke and intrinsic Gauss curvature Ki with normal n. So if we take the unit normal map and use it to define Ke of x like this, and Ki is basically Ke divided by the norm of the normal. That gives us the intrinsic and the extrinsic. And with this formula, the Gauss-Bonnet integral is a sector integral theorem. So let's just get into some of these examples. So here's an example of a torus, and we use the normal norm map to color it basically. So like normal norm, you could plug torus, the tor object into it, or when you want to visualize it, you can plug it into the mesh function, okay? Or mean curvature. That one takes a little bit longer the first time at least to calculate it. Or the sine of the Gauss curvature. Some people find this interesting because it's the sine of the Gauss curvature changes on the torus and this visualizes that sign change. If you're interested in that. Let's define also this wobble So I've previously shown this example before, but I figured I could keep this as an example. So we've defined the function, and then we just apply the function to a torus parameter on a 60 by 60 grid, and then we just visualize it again. But this time, because it's the torus had the function like this, now we changed the function to something different, and it illustrates more of what like here we have the Gauss extrinsic and the Gauss intrinsic. They have different brightnesses. You see that? And the reason for that is because this is a factor, this gets factored out in the intrinsic case, the normal norm. Okay, so the normal norm is present in the extrinsic case and factored out in the intrinsic case. And that's why we have all this going on. Now, another thing that's in differential geometry is when there is a Levi-Civita connection with zero torsion related to a metric tensor, then you have this relation with the Lie bracket, and there exists a Christoffel symbol of the second kind, gamma ijk. And in particular, these can be expressed in terms of the metric tensor G. So this is a formula that has been discussed many times before regarding the Christoffel symbols of the second kind. And then there's the local geodesic differential equations for Riemannian geometry, which apply these Christoffel symbols. So we're gonna do this in an example here. We're gonna continue from the previous example. So this is the intrinsic metric. So if we pick like 2 points on here, on the like 1.2, 1.3, that gives us an outer morphism of the metric tensor at that location, okay? And then this calculates the Christoffel symbols of the second kind. So in order to solve the local geodesic differential equation, we need an initial condition for the differential equation solver. And that's what we're going to create right now. And we're going to use these Christoffel symbols Then we're gonna pick a point on the parameter space. Then we're gonna pick a direction or a vector. Then we're gonna pick a time, a maximum time for the integral. Hmm? Oh, we forgot to do using adapode. Okay, so there we go. So that's produces a geodesic condition. And that gives us the solution there. So now what's interesting is that the actual solution to the differential equation, the geodesic, it was in the two-dimensional parameter space, and it's only when we apply the torus back on it that we get the three-dimensional result back. So so it solves it in using the intrinsic metric, right? So it would appear that its length is, 74, but that's not correct. Let's define this right here. I can type that out. It's not a big deal. All right. Oh. So what's going on here is we've defined another TensorField, Sol M, and this has the intrinsic metric built into it, okay? And so when we take the total arc length, I've demonstrated this before in another YouTube video. When you take the total arc length of Sol M, that gives you the same total arc length as the solution on the torus. So using the intrinsic metric. So this is like a line, a two-dimensional line that goes through a two-dimensional space having a metric tensor. So at each point along the line, there's a metric tensor, and as it goes through this two-dimensional torus space, it has when you take the integral, you have to take the metric tensor into account. And so the total arc length of that curve can contain that intrinsically. So you can either do it in the Euclidean metric, in three-dimensional Euclidean metric, or you can compute the arc length with in the space with non-Euclidean metric. And the formalism here allows you to do like a fully non-Euclidean, metric that varies from point to point, like this, the metric tensor on this, and this can be any general surface. Okay, let's look at the lines of the arc length. Yeah, and there we can see that what the difference is between the apparent arc length and the actual one. All right, so but the thing is, this can be any numerical surface that we calculate these geodesics on. Like we happen to be using these formulas to create these surfaces, but they can just be any numerically generated surface. Like it doesn't have to be generated from a nice function. Like, but here's an example with the FrameBundle. So we compute the Christoffel symbols on the FrameBundle. And then we set the geodesic initial condition. Select a point and a direction. Select the time duration. And now we have our initial conditions specified. And wow, I mean, look at this initial condition. It's got a lot of data inside of it. Oh, I gotta capitalize that. Forgot the X. Okay, so that produces the geodesic on the FrameBundle. But what we'd like is to visualize it on the FrameBundle. So there you go. And let's look at the wireframe. So this is a one-sided surface, and even though it's a one-sided surface, we can solve the geodesic differential equation on it, and it just keeps going on the topology. And although you could reach some kind of a stack overflow limit if you extend the time duration too long on this type of topology, the way it's currently implemented at least. And you can of course look at the normal norms. So yeah, and then we can put the geodesic line oh there you go. So we can see the line. Maybe, I don't know if red is a good color. White. Yeah, so we can see the geodesic on the surface here. And we colored the surface using the curvature. So that's a geodesic on the climb model, and you can, you know, change the initial conditions and all that, and try out different integrations and so on. And you can do it on any arbitrary shape, any topological kind of shape, parameterized like this, or whatever. Or let's do the upper half plane intrinsic hyperbolic Lobachevsky metric. So there's this kind of half plane function that you can define. Yeah, let's just oh, do I not have Z4? Oh, was that capital? Oops. Z4. Z5. All right. So we can put like lines of Z1. Oh no, we don't want to put semicolon afterwards. Suppresses the plot. So this is just an example of trajectories in the hyperbolic plane, like geodesics on the hyperbolic plane using an intrinsic metric. Using this technique, you know, it's just another example of demonstrating different ways you can calculate different things. Let's move on to the next thing for the integrals. Length of a line, area of disk, and volume of a ball. So let's take a look at this here. Let's create some kind of like lin space type of thing. From -2 oh, I need the equal sign, of course. Yeah. Then we can make a diameter like this. Now, what does this actually produce? Diameter. What? Did I spell it wrong? Oh. So this produces a line that's basically that's 1 in the radius of 1 and 0 outside of that. Okay, so we want to compute the integral under of that. So let's look at the Darius example. So the Cartan abstractions enable easily integrating this differential equation here. So we're gonna load Adapode. So now we have this line here. And we're gonna find the Darius equation. So that's the solution to the Darius equation using that initial condition. It's a very nice little solution right there. One thing I didn't put into the paper, but you can do here is so there you go. So the bishop frame example, as an alternative to the standard Frenet style unit frame, the bishop unit frame takes a space, curve, and an angle as an argument. So it has an optional angle as an integration constant, modular rotation of the tangent axis. What is going on? So there we can see what a bishop frame looks like on this curve. Let's continue on to the final example here. So Stokes' theorem. So we consider a paraboloid s equals gamma of x bound by a compact support disk of radius 3 with a circle f of 0 to 2 pi, which is the boundary of s, and this vector field f. So this is just a nice example that we're gonna take a look at right now. So we're gonna produce a square and a cube. And now this is the compact support disk. So we have this disk. This just ensures that we're within the radius of 3, okay? So this is, that's why we have the disk here, okay? And then we're gonna define the paraboloid. And then define what S is. So S is this paraboloid restricted to the circle, right? So we're just cutting it off right there where the circle is. Then we define chain f of x. Yeah, so I already plotted that, right? And then we can add these scaled arrows on it. All right, so those are some unit normals right there. Okay, and then this is the stream plot that's around. This is the vector field that's around this paraboloid. And now what we want to do is we want to calculate this integral here. So this is integral the of the curl in terms of the normal. So this is a surface integral. So we can apply the curl to f on the cube. and then evaluate that on S. And then integrate that. And we get 56.5474. Then we'll do an integral around the circle. And now we can integrate this as a line integral. We can, the integral from 0 to 2 pi of f of t and f prime of t. So f dot t all right, let's integrate this. All right, so now we computed this integral in two different ways, 56.547. Now the exact answer is supposed to be 18 pi, 56.5486. So yeah, it's a nice integral approximation. We have these two different integrals, and we can see that the result is the same. And we computed it numerically using these TensorField representations. So you could technically verify this using just any general tensor fields. It doesn't have to be generated from a paraboloid that's like a nice formula like this. And it doesn't have to be a vector field that has a nice formula like this. These methods work in general just using any FiberBundle representation that's used here. So yeah, so that's a nice example. Both integration techniques come out to the same answer. This is called Stokes' theorem, a special case of the more general Stokes-Cartan theorem. So I thought that's a nice example to wrap things up with for now.